Good morning, dear students. Today, let us discuss the concept of rocket propulsion. First, we will look at the thrust force due to gases on the rocket. So, what is the force that these ejecting gases exert on the rocket? We will look at that in the first part. Next, we will look at rocket equation, which is nothing but the velocity of the rocket as a function of time. So what is this velocity of this rocket as a function of time? We'll be looking at it in the rocket equation. The third topic we'll be looking at is single stage and multi-stage rockets. So here this is called the first stage, the second stage, the third stage. So we'll be looking at the significance of these stages in rockets. Next, we will look at fuel used in rockets and what is the significance that the type of fuel has on rocket propulsion. We will have a look at that. After the concept, I will discuss one question each of board exam level, JEE Mains and NEET level, JEE Advanced level and Olympiad level. So totally I'll be discussing 4 questions after completing this concept. Let us now find the thrust force due to the gases on the rocket. So due to the gases which are being ejected here, what is the thrust force on the rocket? Before moving forward, let us look at some important terms. So the first is mass of fuel burnt per unit time. We will take this as lambda kg per second. So in 1 second, how much fuel is burnt or how much of the gas is ejected is this lambda kg per second. The next term is exhaust velocity of gases, which we will take as Vex meters per second. An important point is that this exhaust velocity is measured relative to the rocket. So this Vx is a velocity which is with respect to the rocket. Let us move on to the derivation of thrust force on rocket. So let us consider two instances, one at time t and the other at time t plus dt. At time t, the mass of the rocket plus the gases is m and its velocity is v upwards. At time t plus dt, a mass dm of the gas is ejected outside. So at time t plus dt, the mass of this rocket is m minus dm and its speed increases to v plus dv. The velocity of the burned gases is v exhaust with respect to rocket. So with respect to ground, using relative velocity concept, we can say it is v exhaust minus v. For now, we will assume there is no gravity. So as there is no external force on the rocket plus gas system, the momentum of the rocket plus gas system is conserved. So the momentum of this rocket plus gas system at time t will be equal to its momentum at time t plus dt. So we can say initial momentum equals to the final momentum. Initial momentum is mass into velocity m into v, and final momentum from here we can say is that for the rocket it is m minus dm into v plus dv, and for the gas which is ejected it is dm into v exhaust minus v. Now we will expand the RHS and we will get m into v equals to m into v plus m into dv minus dm into v minus dm into dv minus dm into v exhaust plus dm into v. We can cancel m into v and m into v here, and minus dm into v and plus dm into v we can cancel. As dm into dv is a very small quantity, we can assume that this is 0. So the expression we get after this is m dv minus dm into vx equals to 0. I am dividing this whole expression with dt. So we get m dv by dt equals to dm by dt into vx. This expression dm by dt into vx, we can write dm by dt as lambda. So dm by dt is the rate at which the fuel is burnt. So we have taken that as lambda. So we get this as lambda into V exhaust. This term m dV by dt is nothing but the net force acting on the rocket. So we can say this is a net force equals to lambda into Vx. So the final expression we get here for the thrust force which is acting on the rocket in the upward direction equals to lambda times exhaust velocity of the gases. So this is an important result and you need to remember this result. Next, we will have a look at the rocket equation, and this rocket equation gives us the velocity of rocket as a function of time. Let us define few terms before going to the rocket equation. So during launch, the initial mass of the rocket is m0. We will take mass of the rocket at time t as small m, which is nothing but m0 minus lambda into t. We have discussed lambda is the rate at which the gas is burned per second. So if the rocket loses lambda kgs per second, after time t it will lose lambda into t kgs. So at time t its mass will be m0 minus lambda into t. During launch, let us take the initial speed of the rocket as 0 and the speed of the rocket at time t is v. Next, the thrust force acting on the rocket equals to lambda into v exhaust, and this force acts in the upward direction. So the net force acting on the rocket is lambda into v exhaust in the upward direction. We can write F net as m times dv by dt equals to lambda into v exhaust. We can write this mass m at time t as m0 minus lambda t into dv by dt equals to lambda times v exhaust. I will take m0 minus lambda t to the RHS and we get dv equals to lambda v exhaust into dt by m0 minus lambda into t. Let us integrate on both sides. At t equals to 0, the velocity of the rocket was 0, and at time t equals to t, the velocity of the rocket is v. See, the rocket equation here is nothing but the velocity of rocket as a function of time. Integrating this expression, we get v minus 0 equals to lambda v exhaust into ln m0 minus lambda t from t equals to 0 to t equals to t into minus 1 by lambda. We can cancel out lambda and lambda here and we get the expression as v equals to v exhaust ln m0 minus lambda t. I'm taking out this minus and writing t initial limit and 0 final limit. So by applying the limits, we get v equals to v exhaust times ln of m0 divided by m0 minus lambda t. So this equation here is called as the rocket equation. So I want you to remember this equation also. See, in this equation we have not considered the gravitational force. So this rocket equation is applicable for rockets in space where there is no gravity. Let us now extend the rocket equation, and in this case we'll consider gravity also. In the previous case we considered only thrust forces on the rocket. In this case you see we have put an additional force which is the gravitational force on the rocket. So we have two forces acting on the rocket right now. One is the thrust force and the other is the gravitational force. So the net force acting on the rocket is thrust force minus the gravitational force. So we can write net force equals to mass into acceleration, which is equals to thrust force minus mg. Next we are dividing the LHS and the RHS with small m. I am writing the acceleration as dv by dt, and dt I am taking to the RHS and I am integrating. So this is very similar to what we did in the previous case. We are only getting this gt term extra here. This gdt term is a extra term. So if we include gravity, we get the equation as v equals to V exhaust ln m naught by m naught minus lambda t minus g into t. There are few assumptions which we are making here while coming up with this equation. The first assumption is we have assumed that small g is constant, and that is why we have got integral g dt as gt. Okay, as the rocket is going up, the small g value varies considerably. Even low earth orbit, if you take, it is 1/3 the radius of earth, so the small g value changes considerably. So that's the first assumption that we are making, is g value is a constant. Now when a rocket is going up, it is not always in the vertical position, it might be tilted also. So when it is tilted, the correct equation mg, it would not be mg, but it would be a component of mg if the rocket is tilted. Okay, so here you will not have only mg, you will have it as mg component. So might be mg cos theta you will have, and the theta will keep on changing when the rocket tilts. Okay, so the second assumption that we have made here is the rocket is moving always vertically up. Okay, so two assumptions. The first, small g is constant. The second, the rocket is moving vertically up. And with these two assumptions, we come to this equation. Let's move on to the next topic, that is single and multi-stage rockets. Let us first understand why we have come to the concept of staging of rockets. So we have derived the rocket equation, which was the velocity of the rocket equals to the exhaust velocity of the gases into ln m naught by small m. Let us understand these two terms, m naught and m. This m naught is the initial mass and this small m is the final mass. So this initial mass equal to mass of the structure plus mass of the fuel plus mass of the payload. So first is mass of the structure. So you can say all this is the structure of the rocket. This includes these fuel tanks, these engines. So this is the mass of the structure. Next is mass of the fuel. So how much fuel you have inside this rocket is the mass of the fuel. This fuel is what keeps getting consumed. The next is mass of payload. So let us understand what is this payload. You see this rocket here. In this rocket, we want to put this satellite into orbit, which means in the orbit only this satellite will be there. The rest all will not be there in the orbit. So all this is just the structure. This is the main thing that we want to put in orbit. So this is called the payload. 99% of the rocket consists of structure and fuel. Only 1% is the payload, which means if you want to put 1 kg of payload into orbit, you require 99 kgs of structure plus fuel. This is the reason why space programs are very expensive. Next, the small m here is the final mass when all the fuel has burnt out. So the final mass small m is mass of structure plus mass of payload. So finally the fuel is burnt and you just have mass of structure and mass of payload. Now let us understand why staging is important. Let us consider there is fuel located separately in these three tanks. Okay, so there is a fuel tank here, there is another fuel tank here, and there is another fuel tank here. Now the fuel which is there in this tank increases the velocity of the whole rocket to, let us say, some value v1. Now after the fuel in this tank gets over, now the fuel in this tank starts getting used up, right? Now the fuel in this tank is used to increase the velocity of the rocket of this part plus this part plus this and the payload. Okay, the fuel in this tank is used to increase the velocity of the whole rocket. Now if after the fuel in this tank has been used up and if this tank falls off or if this tank separates, then these three are still joined and these three are going up in space. So the fuel which is there in this will be used to take these three structures into space. Okay, you see in this case the fuel in this tank is used to take the whole structure into space and the increase in velocity is less. But if this breaks off, let us say if this breaks off, the fuel in this tank is used to increase the velocity of only these three parts, and it can increase the velocity much higher. Once the fuel in this tank gets over and this also falls off, the fuel in this tank will be used to increase the velocity of these two parts. So what we are doing in staging is we are removing the unnecessary structure in the rocket, and thereby we are decreasing this mass m. Okay, see, we are removing unnecessary structure and decreasing the small mass m. As you decrease the small mass m, this value increases and this v also increases. So if the whole of this rocket, the structure plus the payload, goes into the outer space, we say that it is a single stage rocket. But if parts of the rocket fall off, like these fuel tanks fall off after the fuel gets over, this is called a multi-stage rocket. So this is a single stage rocket and this here is a multi-stage rocket. Let us now discuss the final velocity of multi-stage rockets. So we have a rocket here, and this is the first stage, this is the second stage, and this is the third stage. Our job would be to calculate the final velocity of this payload or this satellite when it reaches its orbit. We have discussed in the rocket equation V equals to V exhaust ln m naught by small m naught, where capital M naught is the initial mass and small m naught is the final mass when the fuel is over. So let us consider this rocket here. This is a multi-stage rocket, and this m naught is the total mass of this rocket. Okay, the mass of the structure plus payload plus the fuel inside. Now let us see what is the small m naught. So have a look here. Now all the fuel in this tank that you see here is burnt. Okay, now this small m naught is the total mass of the rocket now. So what is the total mass of the rocket now? The initial mass minus the mass of the fuel burnt. So right now this rocket has a velocity v exhaust ln m naught by small m naught. Next, what happens? The fuel in this has to get used up, which means this structure is removed. Now this part of the rocket is moving with V exhaust ln capital M naught by small m naught. Now this engine fires up, and again we will use the same rocket equation to calculate the velocity. Now due to this engine firing up, the velocity of this part of the rocket increases by V exhaust ln capital M1 by small m1. This capital M1 is mass of the structure plus payload plus the fuel which is present inside. Now the engine fires up. Now this small m1 is the mass of rocket now. Okay, this is nothing but capital M1 minus the fuel which has got used up here. Now this stage separates. Now this stage gives an additional velocity V exhaust ln capital M2 by small m2 to this rocket. The mass of the rocket right now, is capital M2. Now the engine fires up. The mass of this rocket now, after this fuel is used up, is small m2. Now this part detaches itself from the payload. So now this is the final expression for the velocity of the payload. Let us have a look at the schematic once again. Let us now take a look at few questions. So I want you to go through the question and give it a try initially, and if you are not getting the answer, then you can have a look at the solution. So the first question is of board exam level. So let us analyze the question. Rocket fuel is capable of giving an exhaust velocity of v equal to 2.4 kilometers per second in the absence of any external forces. So he has given here that this V exhaust equal to 2.4 kilometer per second. As he has mentioned no external forces, so we can say that there is no gravity involved here. The fuel required per kg of the payload to provide a final velocity of 12 kilometers per second to the rocket is dash. So he has given here that the final velocity of this rocket is 12 kilometers per second. The question is asking is what is the fuel required per kg of the payload. So we use rocket equation here, which is V equals to V exhaust ln capital M naught by small m naught. So capital M naught is mass of fuel plus mass of payload, and finally all the fuel is used up and you have only the payload mass. As he has not given us any staging here, we are taking the mass of the structure in mass of payload only. So that is why I have not mentioned the extra mass of structure here. I have included it in the payload itself. Substituting these values in the rocket equation, we get 12 equals to 2.4 times ln of mass of fuel plus mass of payload divided by mass of payload. Now he has mentioned per kg of payload, so I've just substituted this MP as 1 kg. So I get 12 equals to 2.4 times ln of mass of fuel plus 1. Next we get 5 equals to ln of m fuel plus 1. So finally we get mass of fuel as e power 5 minus 1, which is approximately equal to 147 kg. So per kg of the payload, the fuel required is 147 kgs. Let us have a look at a question of NEET and JEE Mains level. A rocket of initial mass 6000 kgs ejects gases at a constant rate of 20 kgs per second with constant relative speed of 8 kilometers per second. So we have a rocket here. Its initial mass m0 is 6000 kgs. The rate at which gases are ejecting is 20 kgs per second, which is lambda. The exhaust velocity of the gases with respect to the rocket is 8 kilometers per second. I'm writing this as 8000 meters per second. The rocket starts from rest at t equals to 0. So this rocket here starts from rest at t equals to 0. If A0 denotes the acceleration of the rocket in absence of gravity. So on this rocket that you see here, there is only the thrust force and there is no gravitational force, and the acceleration of this rocket is A0. And Ag denotes the acceleration of the rocket in presence of gravity. All the given data is the same in this case, but in this case there is a gravitational force acting. So you have thrust force and you have gravitational force, and the acceleration of this rocket is Ag. Find the ratio A0 by Ag at t equal to 100 seconds. So we need to find the ratio of acceleration of these two rockets at t equals to 100 seconds. So the net force on this rocket is capital F equal to lambda into Vx. Only this force is acting. So at time t equal to 100 seconds, if the mass of the rocket is small m, we can write the net force on this rocket is lambda into Vx, which is equal to small m into A0. See, this small m is capital M naught minus lambda into t. Taking small m to the RHS, we can write A0 equals to lambda V exhaust divided by small m. In the second case where gravity is present, we can write the net force on this rocket as lambda Vx minus mg. So I'm writing the net force equals to lambda into Vx minus m into g. So we can write this as m into Ag equals to lambda V exhaust minus small m into g. We will take the small m to the RHS and we'll get Ag equals to lambda V exhaust by m minus G. So we find the value of A naught and we put in the values of lambda, which is 20, V exhaust, which is 8000, and small m is m naught minus lambda t. So m naught is 6000 minus lambda is 20 into at time t equals to 100 seconds. So calculating, we get A naught equal to 40 meter per second square. Ag is lambda Vx by m minus G. This lambda Vx by m, I'm writing it as A naught. So Ag is A naught minus G. So he has given here, take G as 10 meter per second square. So we get Ag equal to 40 minus 10 equal to 30 meter per second square. So finally we get A naught by Ag equals to 4 by 3. Let us now look at seating position for astronauts in rocket. In the previous question we had got A naught as 40 meter per second square and Ag as 30 meter per second square. These are very high values, and in a manned mission the maximum acceleration is 25 to 30 meter per second square. When the rocket is being launched, if the astronauts are in this position as shown, what happens is, due to huge acceleration upwards, blood gets collected near the feet and there is very less blood available for the brain. So at such high accelerations, if there is less blood available for the brain, the astronauts might fall unconscious or they might feel giddy. So let us have a look at the sitting position of astronauts in a rocket. So have a look here. So when the astronauts are in this position, okay, when the astronauts are in this position, we can ensure that this problem does not happen. So this is how astronauts are seated during the launch of the rocket. Let us now take a look at a question of JEE Advanced level. Let us first analyze the question. N people, each of mass m, are standing on a railway car of mass capital M at rest. So there are n people here of mass m. They are standing on a railway car of mass capital M, which is at rest. I have just taken 3 people here, okay, so that you can visualize it. Next, the car can roll on the tracks without friction. So this railway car here can roll on the tracks without friction. People jump off one end of the car with a horizontal velocity component u relative to the railway car. So these people here jump off the railway car with a horizontal velocity component u relative to this railway car. See, this is a multiple correct option question. So he has given 2 cases here. After analyzing these 2 cases, I'll show you the options. Case 1. People jump from the car one by one. So one after the other, these people jump from the car. Let us have a look at the schematic. So people jump off the car one after the other. And you can see that the cart moves in this direction. Case 2. People jump off the car at the same time. So all these people jump off this railway car at the same time. So let us have a look at this. So all the people jump off the cart in same time and the cart moves in this direction. As this is a multiple correct answer question, let us analyze each option and see if it is right or wrong. So the first option is the final velocity of car in case 1 is given by u small m by capital M summation I equals to 1 to capital N I divided by 1 plus I small m by capital M. So let us again have a look at the first case. Let us first calculate the velocity of this cart after the first person jumps off. So say the velocity of the car after first person jumps off is u1. So this is the initial case. The railway car and the persons on the railway car are at rest. Finally, the first person jumps off the car and the car gets a velocity u1 to the right. So the car and the people on the car, see, one person of mass m has jumped off, right? So the remaining people on the car are n minus 1 into m. Okay, so all this car and these people have velocity u1 towards right, and this person of mass m who has jumped off has a velocity u minus u1. See, he has said u with respect to cart, so with respect to the ground, this person has a velocity u minus u1. So we can say, as there are no external forces acting on the system, initial momentum equals to final momentum. Initially, the speed of all these people plus the car is 0. So the initial momentum is 0. Finally, these people plus car have speed u1 in this direction. So I'm writing the total mass of these people into u1. This person has his momentum towards the left. So I'm writing minus m times u minus u1. Now expanding this equation, we get this. So simplifying this, we get u1 equals to mu by capital M plus n into m. Which means after the first person has jumped off, this is the velocity of the cart. Say the velocity of the car after the second person jumps off is u2. So final velocity of this car is u2 after the second person jumps off. Initially, the car plus the persons who are there. One person has jumped off, so the total mass is n minus 1 into m. It was going with speed u1, and now finally this is going with speed u2. As there are no forces acting on the system, we can conserve the momentum initially and finally. So we can write down initial momentum equals to final momentum. So initially the momentum is this total mass into u1, which I have written here. Okay, and finally the momentum is this total mass here into u2 minus this mass into its speed here. So we get this equation in the RHS. Now we need to calculate for u2. As we can observe, this equation is very big, and to calculate u2 from this equation would be very inconvenient. So as the equation seems bulky, let's try another approach to make it simple. So let us try another approach so that we can simplify this and we get the answer in a very simple steps. So let us try a much simpler method. In this method, we will look at the cart from a reference frame moving with speed u1. So let us say the reference frame is moving with speed u1. We will look at the car from this frame. So this cart is actually moving with speed u1. If we look at it from a reference frame also which is moving with u1 in the same direction, this cart will seem to be at rest. In this reference frame, the cart seems to be at rest initially. So initially the cart seems to be at rest. Finally, with respect to this reference frame, the cart speed is u dash. Okay, in this reference frame, the cart speed is u dash. So in this reference frame, as there are no external forces acting on the system, we will conserve the momentum of this system. So we can write initial momentum equals to final momentum. So as initially it is at rest, the initial momentum is 0. Finally, this car and this n minus 2 into m have a speed u dash. So we will write n minus 2 into small m plus capital M into u dash minus this person here has a speed u minus u dash to the left. So minus m into u minus u dash. So when we expand this RHS, we get this equation here. We can cancel this mu dash and minus 2 mu dash. This becomes minus mu dash. So we get u dash equals to m into u divided by n minus 1 into m plus capital M. If the speed of the cart with respect to the reference frame is u dash, then the speed of the cart with respect to the ground is u1 plus u dash. See, the reference frame was moving towards right with speed u1. So that is why with respect to ground it becomes u1 plus u dash. So the final speed of the cart u2 after the second person jumps off is u1 plus u dash, where u1 we have calculated as mu divided by nm plus capital M, and u dash we have calculated as mu divided by n minus 1 into m plus capital M. So this method of taking a reference frame which is moving with speed u1 and then solving this is much easier than solving it in the ground frame. See, now we are seeing a pattern here. Okay, now you can guess what will be u3. u3 will be this term plus this plus another term which will have n minus 2. Okay, so now let us write down what will be u3, the speed of the cart after the third person jumps off. So we can write u3 as u2. See, this whole thing is u2 plus another one term which will have a n minus 2 here. Now let us write un, which is the speed of the cart after all the persons have jumped off one by one. So we can write un as, see, mu by nm plus m is the first term. So first term I'm writing it here. You see, first term, see, all these are the same. Mu is the same and capital is the same everywhere. Okay. The only thing that is changing, the only term that is changing is this one. So first term is n minus 0 into m. Second one is n minus 1 into m. The third term is n minus 2 into m. So we can say the nth term will be n minus 1 into m. So this will be the nth term. Okay. So we can write this un as mu by capital M into summation I equals to 1 to capital N, 1 divided by 1 plus Im by capital M. Okay, so just see this term you see, okay, mu divided by n minus n plus 1, right? So this is nothing but 1. So small m plus capital M. The next term will be what? 2 small m plus capital M, and so on, n small m plus capital M. Okay, so that the same way here, I is 1, it will be m, I is 2, 2m, and so on till n times small m. Now to get this term, what I have taken is I have taken this capital M common in the denominator, and that is why I am getting 1 plus I into small m by capital M. So in the first option he had given that the final velocity is um by capital M. So this is fine, and here 1 plus Im by capital M also, which we have got. In the numerator he has got a I extra, okay, but it should be 1. So first option is not the correct option, it is a wrong option. Let us now move on to option B. Assume that the total mass of all the people in the car equals that of the car. So he's saying the total mass of, there are n people here, so the total mass of this equal to mass of the car. So we can write n into small m equals to capital M. The ratio of final velocity of car in case 1 to that in case 2 is 2:2. So for very large value of n, we need to calculate the final velocity of car in case 1 and in case 2, and we need to take the ratio of these two. Recalling, in case 1, the people jump one after the other. So while solving for the first option, we had got what is the final velocity of the cart. This expression we had got. From here, we'll substitute small m by capital M equals to 1 by n. So we'll substitute this in this equation. So in this step, we have written m by capital M as n, and m by capital M here we have written as n. I have written here capital N and here I am writing small n. So please don't get confused. It is the same thing. In the next step, I am taking this I by n equal to x. So I by n equal to x. And next I am differentiating. I am writing di equals to n dx. See, what I am doing is I am converting this summation here to an integral. So now I have converted this into an integral. U remains u. 1 by n. We can write 1 by n here as dx. So 1 by n I have written as dx. See here, no, di I have written it as 1 because we are incrementing I by 1 to n. Okay, so the change in I is 1. So I have written it as 1 here. Next, I by n, here I am writing it as x, because we have taken I by n as x. Next, let us see the limits. Okay, when I equals to 1, so put I equals to 1, we get x equal to 1 by n, and this is almost, you can say, very small, 1 by n, as n is very large, 1 by n is very small. So I'm putting the initial limit of x as 0. When I equal to n, so we are putting n here, the final limit x is n by n, which is equal to 1. So integrating this, we get u ln 1 plus x, initial limit 0 and final limits 1. So for case 1, after all the people have jumped, we get the final velocity of the cart as u ln 2. Let's now look at case 2, where all the people jump from the railway car at the same time. So let us have a look at this once again. Say the final velocity of the car in case 2 is v. So the velocity of these people who have jumped all at once will be u minus v. So as no external forces are acting on the system, initial momentum equals to final momentum. Initially the cart was at rest and the people were at rest, so initial momentum is 0. And finally the cart speed is v. So m into v minus nm times u minus v. The velocity of these people with respect to ground is u minus v. We have n into m equals to capital M, because the mass of the people equal to the mass of the car. And if we put it here, we get v equals to u by 2. So the final velocity of this cart when all people jump at a time is u by 2. So the final ratio, that is velocity in case 1 to the final velocity in case 2, is u ln 2 divided by u by 2. So finally we get the ratio as 2 ln 2, and that is what he has given in option B. So option B is the correct option. In option C, he has given the final velocity of car in case 1 is greater than that in case 2, and in option D he has given the final velocity of car in case 2 is greater than case 1. So the ratio, we get 2 times ln 2, which is nothing but 2 into 0.69, which is equal to 1.386, which means the final velocity in case 1 is greater than case 2. So we can say option C is also the correct option. So finally the correct options are B and C. Let us now take a look at a question of Olympiad level. This is a comprehension type question. So first there is a comprehension given and there are 5 questions asked. So we need to answer each of the 5 questions. Let us first analyze the question. This problem is designed to illustrate the advantage that can be obtained by the use of multiple stage rockets instead of single stage rockets. So we have discussed already why multiple stage rockets are more effective than single staged rockets. Suppose that the payload, example space capsule, has mass m and is mounted on a 2-stage rocket. So this is the payload which we have here, and the mass of the payload is small m. This payload is mounted on a 2-stage rocket. So this is a first stage and this is a second stage. The total mass, both rockets fully fueled plus the payload, is capital N into m. So the total mass of the payload plus these 2 stages plus the fuel which is contained in these 2 stages is capital N into m. The mass of the second stage rocket plus the payload after first stage burnout and separation is small n into m. After the first stage is separated from this rocket, the mass of the second stage plus payload plus the fuel inside the second stage is small n into m. In each stage, the ratio of container mass to initial mass, that is a container plus fuel, is r. So he is giving us that in each stage, the fraction of container mass is r. Okay, the mass of this, whatever structure is there here, divided by mass of the structure plus mass of the fuel is r. And the exhaust speed is v, constant relative to the engine. So the exhaust speed of this gases is V, which is constant relative to the engine. Note that at the end of each state, when the fuel is completely exhausted, the container drops off immediately without affecting the velocity of rocket. Now the fuel in first stage is over and the velocity of this rocket is 10 kilometers per second. I'm just taking a random value here. Now after this first stage detaches and drops off, still the speed of the remaining rocket is 10 kilometers per second. So the dropping of this stage does not affect the velocity of the rocket. Ignore gravity. First question. Obtain the velocity v of the rocket gained from the first stage burn starting from rest in terms of v, capital N, small n and r. At this instant we can see that the fuel is over in the first stage and the first stage burn has occurred. So what is the velocity of the rocket now is the question. From the rocket equation we have speed of the rocket equals to exhaust speed ln m initial divided by m final, where m initial is the initial mass of the rocket and m final is the final mass of the rocket. The initial mass of the rocket is capital N into m. So it's given very initially with the whole rocket plus the fuel inside equals to N into m. So the initial mass of the rocket is capital N into m. See, after the first stage burn, what happens? The fuel inside this first stage is consumed. So the final mass will be total mass minus mass of the fuel in first stage. In the question he has mentioned that mass of first stage container equals R times total mass of first stage. So mass of fuel in first stage will be 1 minus R times total mass of first stage. So mass of fuel is 1 minus R times total mass of first stage is total mass of rocket, which is capital N into M, minus total mass of the payload plus second stage, which is small n into m. So finally the mass after the first stage burn will be total mass minus mass of fuel in the first stage. So total mass is capital N into m minus mass of fuel we have found here. So just expanding this, we get this as the final mass. We can cancel out capital Nm and capital Nm. So finally we have Mi as capital N into m and Mf we have this value. We will put these both in this equation and finally we get the velocity of the rocket after first stage burn is V equal to V exhaust ln capital N divided by capital N into R plus small n into 1 minus R. See, in the question he has given this as small v and this is capital V, so that there is no confusion. I am just writing this as Vx, that is V exhaust. So finally this is the answer to our first question. The next question is obtain a corresponding expression for the additional velocity u gained from the second stage burn. So we will again use the rocket equation. The additional velocity for the second stage is V exhaust ln Mi by Mf, where Mi is the initial mass now, okay, when there is this payload second stage container with the fuel. Now all the fuel has burnt out. Now the total mass of this rocket is Mf. So initial total mass is small n into m. So the total mass of this with fuel in the second stage is small n into m. So final mass equals to total mass minus mass of fuel in second stage. So we saw that mass of fuel is 1 minus R times the total mass of the second stage. So the total mass of the second stage is Nm, which is the total mass of the rocket minus mass of the payload, which is small m. So final mass of the rocket is total mass minus mass of the fuel, which we have calculated here. Expanding this, we get this equation, and here we can cancel out Nm and Nm. So substituting Mi and Mf in this equation, we get U equals to V exhaust ln n divided by m into 1 minus r plus n. So this is the final answer to our second question. Let us move on to the next question. Adding v and u, you have the payload velocity w in terms of capital N, small n and r. So w is the final velocity of the payload. This is equal to v plus u, which we have calculated in part A and B. Okay, so these are the expressions for v and u. Taking capital N and r as constants, find the value of small n for which w is maximum. So taking capital N and r as constants, we need to find small n such that the final velocity of the payload is maximum. For this maximum condition, obtain u by v. So at the value of small n, where the w is maximum, we also need to calculate u by v. So we can write this w as this is vx ln of a plus ln b, which is ln a into b. Now for this whole expression to be maximum, see this is a constant. So this, if this is maximum, then w will be maximum. So for w to be maximum, f of n, which is this function, must be maximum. So I'm writing this function as f of n equals to small n divided by capital NR plus small n into r dash, where I'm replacing this 1 minus r with r dash. Okay, and divided by nr plus r dash. I'm just multiplying and dividing this equation with r dash and r. Okay, so I'm trying to get my equation in a much simpler form. To simplify it further, I'm taking capital NR by r dash as a and r dash by r as b. So what we'll do is we'll differentiate this equation now and make it 0, and then we'll get the maximum value of f of n. So in the next step, we are differentiating this and equating it to 0. So this expression equals to 0. If we expand this, we get this expression plus na minus na cancels, plus nb minus nb cancels, and we are left with n square plus ab minus 2n square equal to 0. So we get n square equal to ab, or n equal to plus or minus under root ab. We had taken a as capital NR by r dash and b as r dash by r. We take only the positive value, as n cannot be a negative value. So we get small n equals to root n for w to be maximum. So for final velocity of payload to be maximum, we get small n equals to root capital N. In the same question, we need to find the value of u by v. So I have written u by v here. The v exhaust term has got cancelled. See, we have got small n equals to root capital N. I can also write capital N equals to small n square. So here, in place of capital N, I'll put small n square. In place of capital N, I'll put small n square. Here we can cancel out n in the numerator and denominator. So we get this numerator equal to denominator, and we get u by v equals to 1. Which means when velocity of payload is maximum, the velocity that the first stage gives to the rocket equals to the velocity that the second stage gives to the rocket. Let us move on to the next question. Find an expression for the payload velocity ws of a single stage rocket with the same values of capital N, R and V. So we have a single stage rocket here, and the total mass of the rocket is capital N into M, and mass of the payload is small m. Again, we will use the rocket equation, which is V equals to V exhaust ln mass initial by mass final. M initial is total mass of the one stage rocket, which is equal to capital N into M. So written here capital N into M. And M final is the final mass of the rocket after the fuel has burnt out in the first stage. M final equal to total mass minus mass of fuel which has been consumed. So calculating the final velocity of the payload, he has given it as Ws equals to V exhaust ln capital N divided by capital NR plus 1 minus R. Let us move on to the fifth question. Suppose it is desired to obtain a payload velocity of 10 kilometers per second. So he's saying that the final velocity of this payload must be 10 kilometers per second. Using rockets for which v equal to 2.5 kilometers per second. So this is the exhaust velocity and r equals to 0.1. Using maximum condition of part C, obtain the value of capital N if the job is to be done with a two-stage rocket. So in part C, when we use the maximum condition to find the final velocity of the payload, we got u equal to v. So we can say the payload velocity equals to 2 times u. And he's giving us that this payload velocity equal to 10 kilometers per second. So we got the value of u as v exhaust ln small n by small nr plus 1 minus r. This is equal to 5 kilometers per second. So we put in the value of v exhaust as 2.5 and r as 0.1. So we can write this as n divided by 0.1 n plus 0.9 equal to e square. Solving this, we get small n equals to 25.46 or capital N equals to 648.7. This comes to the end of rocket propulsion concept. I hope you all liked the video, and I hope this video better your understanding in the concept of rocket propulsion. If you like the video, do put a like, share it with your friends and subscribe to the channel. I have put a rocket launch video at the end. Do watch it and enjoy it, and let us meet again in the next video.